Hello everyone, I'm Chaemin from Yonsei University, and this talk I'll present our work on the design and analysis of processing-in-DIMM algorithm, a case study with Chaemin DIMMs. This work is done by my colleagues and my advisor, Professor Yonsei, and this work is also already presented at the Sigma Council 3. So the full paper is on my website. If you're interested, please check my full paper. So Join is a key operation for relational databases, and it is well known to be memory intensive since it accesses throughout the two tables to combine the tuples. So high memory bandwidth is essential for accelerating the memory join, accelerating the memory intensity memory join. However, conventional systems commonly suffer from the limited memory bandwidth because it is hard to achieve higher memory bandwidth over the standard memory channel. So this is also called as a memory wall. So the memory wall has become a major performance bottleneck for accelerating the memory joins. While processing in memory is a promising solution to overcome the memory wall, so PIM can achieve a significantly higher memory bandwidth than over the CPUs. So in conventional system, the data has to traverse a long path from the memory device to the entire cache hierarchy of the CPUs. However, PIM-enabled systems can access data indirectly in the memory device, and multiple in-memory processor can access data in parallel. So by doing this, PIM can exploit the high inter-memory bandwidth and work on the memory wall. So we set our goal as enabling fast in-memory joins on the PIM-enabled DIMMs. And as you can see in the figure, PIM provides 9 times higher memory bandwidth than non-PIM memory. And adding more PIM devices can further increase the memory bandwidth. And it is not bounded to the number of counts of the memory channel, because the data can be accessed in the memory device directly. So PIM can fully exploit the high inter-memory bandwidth when the scalable algorithm is fully uploaded to the PIM. While prior studies already propose several join algorithms to utilize PIM. However, there are 2 key limitations that prevent directly applying PIM join algorithm on the PIM-enabled DIMMs. The first limitation is they commonly focus on 3D stack memory. However, the 3D stack memory have a different architecture with PIM-enabled DIMMs. And second, they rely on site-level simulations, which can be easily enacted on the real system. And there is actually no real-world hardware for the agency. So they commonly focus on 3D stack memory, and they are not publicly available, and they cannot evaluate on the real system. Before moving on to our design, I would like to introduce 3 characteristics of PIM-enabled DIMMs. So the first characteristic is per bank processor. So DIMM has arranged chips and banks in a parametric manner, and PIM-enabled DIMM process places 1 processor per each bank, and there is a working mem, that is a scratch band memory. So IDPs can perform computation and they initiate the data transfer between the working mem and the memory bank. So the example of PIM-enabled DIMMs is the UPMEM DIMMs and the Samsung AX DIMMs. The second characteristic is shared knocking architecture. Shared knocking architecture means that there is no direct communication passes between the banks. So CPU must mediate the data transfer between the source and destination banks. So the working model of inter-bank communication starts with collecting the data from the source banks, and CPU distributes to the destination banks the data. And as you can see in the figure, the working model of inter-bank communication is performed with the granularity of a cache line. And the third characteristic is memory equilibrium. Memory equilibrium means that the sequential data flow gets literally quite wisely across the banks, chips, and banks. And this design is for providing high memory bandwidth by accessing the memory bank in parallel. However, in the case of PIM-enabled DIMMs, this causes a problem because when the data are copied to the destination banks, as you can see, the bank on the chip 0 gets the index of the data 0, 8, 56, and the bank at the chip 7 gets the index of the data 7, 15, and 73. So in the point of view of the in-DIMM processor, they cannot interpret the data directly. So there is a need for cache line transposing for each data, and the UPMEM SDK already implemented for this, for the data store transfer. To further explain the differences with the 3D step memory, the hybrid memory cube is the most popular 3D step memory and has a DRAM banks both in TSPs. And the programming logic is implemented on the bottom logic line. And they strongly assume that the programming logic can access all the DRAM banks with TSPs. So they strongly assume that there are shared memory architecture. However, as I mentioned, PID-Join is a shared locking architecture. So we need the PID-Join algorithm that fits with PID-DIMMs and efficiently utilizing the PID-DIMMs. So we set our first design goal to enable fast in-memory joins on the PID-DIMMs. And we claim that we should satisfy the following design goals to achieve high performance. The first thing is the compatibility with the stock PID-DIMMs, because prior was relying on simulations and only for the 3D step memory. And the second goal is to develop a fast single IDP-Join algorithm. This is because each IDP can access the data stored in the associated bank only. And third, maximizing inter-bank post-spin data transfer bandwidth is crucial because scaling the single IDP-Join to multiple DIMMs and IDPs require fast inter-bank communication method and their bandwidth. So I'll explain PID-Join, processing-in-DIMM join algorithm, with 3 challenges and the following key ideas. Let me first give you the summary of the challenges and the following key idea. So we firstly propose a fast single IDP-Join considering the limited capability of IDPs. And second, we propose rotating tree, overcome the slow interbank communication. And third, we propose another scalar data that mitigate the slow post-spin data transfer. So the entire working model is like that. So firstly, the RNS table are stored in the CPU side, and we perform rank-wise another scalar data to send RNS table to the PID-enabled DIMMs. And inside the PID-enabled DIMMs, they perform a matrix partitioning on the pin side to collect the data, collect the tuples to have the same reading speeds on their memory bank. And we perform auto communication by rotating tree. And we perform a single IDP-Join on the pin side again. And we send back the join result to the CPU. So the first challenge is the limited capability of IDPs. So there is a lack of data kernel support for complex arithmetic operations, such as multiplication and modulo operation. So as you can see on the figure left, the calculation hash function shows your 7 times higher hash throughput compared to the Weber hash, because calculation hash function is constructed based on the XOR based calculation hash, and the Weber hash is based on the multiply. So there is a performance gap between the XOR and multiply, and the random access leads to significant bandwidth degradation. So as you can see here on the right, the random access to the memory bank shows 89% degradation of the memory bandwidth, while working mem only shows 20% degradation. This is due to the raw activation of the DRAM banks, which activates its data at larger granularity than the access size. So our first key idea is optimized single IDP-Join. So this idea is based on the key idea that we need to import the sequential memory access between the working mem and memory bank access, and filtering the random access to the working mem only. So this is the working model of the hash join. So we firstly perform upper processing on the working mem, and we filter the random access to fill in the buckets. And when the buckets are full, the buckets are spilled down to the memory bank, and this can be implemented with the sequential and large access granularity. Then we perform hash table build and throw phases on the working mem only because we already made the partitions for the RNS tables. And also the join result can be flushed out to the memory bank. So by doing this, we can enable fast single IDP-Join, which fully exploits the architectural characteristic of DIMMs. So in the case of nested loop join and sort merge join, so in the case of sort merge join, they have random access behavior on the sorting phase. So we firstly perform a range partitioning on the working map, like join, and we make a partition and so perform a sort merge join by streaming the partitions to the IP. And in the case of nested loop join, they already have the streaming manner for their IP. So we just streaming the RNS buffer to the working map and perform nested loop join. So our second challenge is the slow interbank communication. As I mentioned, there is a need for CPUs to mediate the data transfer between the source and destination banks. And there is a need for transposing for each data to identify the exact data. So the conventional communication working model starts with loading and transposing the tuples. This is performed by the UPMEM SDK. And when the tuples are stored in the host memory, the CPU performs shuffling on the host memory side. And then we perform transposing and storing the tuples to the destination banks. However, this incurs high performance degradation because the transposing operation are performed twice. This incurs a high computation overhead, and there is a shuffling at the middle of the CPU, and this incurs a high, many random access to the host memory. So our second key idea is rotation stream. This idea is based on the key idea that we can use IDPs and CPU both for the communication. And second, we explore the identical data layout of the source and destination banks. So the working model of the rotate starts with the tuple-wise rotation on the host memory side. And we directly go to the vector registers because we don't need to access the host memory because we can stream out the tuples. So we perform byte transposing on the host vector register directly and store the tuples to the destination banks. So by doing this, we can enable fast interbank communication and with a single byte notation, and we can also stream the tuples. Our third challenge is the flow of stream data transfer. So we need to transfer the input and output tuples between the host memory and the key side. And there is a per bank region splitting on the host memory because we need to identify what data need to be copied to the destination banks. So the region 0 goes to chip 0, like this. And the working model of conventional host data transfer start with collecting the tuples from each memory bank, their regions, and construct a cache line, and load it to the vector register, and perform transposing and storing the tuples. However, this working model requires high values degradation because firstly, when we collect the data from different regions, there is a random access behavior on the host memory. And second, there is a redundant load on the CPU side to construct a cache line and load it to the vector registers. To mitigate this, our third key idea is moment scatter, which exposes the fact that joins do not impose pre-ordering on the input and output tuples. So we remove the region splitting on the host memory, but then access the host memory in a streaming manner and directly load into the vector registers and perform transposing and storing the tuples. This is a simplified idea. However, we can eliminate the random access behavior on the host memory, and we remove the redundant load on the host memory side. So by doing this, we can achieve a high bandwidth host data transfer with sequential and large access granular memory access. Then from now on, I'll explain the evaluation results and the conclusion of this topic. So our experimental system consists of Intel Xeon 5222 CPU, and we utilize 4 channels. So in the baseline system, we have 5 standard channels, and for the PIM system, we have 4 PIM channels and 1 for the standard memory. And we have a synthetic benchmark with 32-bit mixture joint keys and supply keys. and we vary the RS ratio, also consider the skew distributions. And we have 4 TPCH cores involving a two-way join. So this is the picture of our system. So in respect to the latency, we can show the speed up for the necessary joins or one join and that's hash join compared to the CPU-based join algorithms. And especially for the hash join, we show up to 2.43 faster join latency compared to the PRHO, which is a sort of CPU-based join algorithm, also called histogram optimized parallel join. And I can say that this can be done by applying data transfer optimization techniques. So with respect to the data transfer optimizations, we can achieve a 6.42 times higher memory bandwidth than the conventional way for the auto communication, and we achieve a 3.91 higher memory bandwidth compared to the conventional way in case of positive data transfer. And this can be achieved by enabling streaming banners with large access rate. This is the result of our evaluation study. So when we nightly apply the single IP join on the P side, there is a slowdown compared to the CPU-based join algorithm. So we accordingly apply the rotating stream and overload error. We can achieve a speed up to 3.03 times speed up compared to the live implementation. And this is the result of the scalability evaluation. So as you can see, the PID-Join can easily scale out with very rank counts. And the PID processing time can decrease because the number of processing elements increases. And there is a little bit latency increment on the CPU processing time because there is some memory paddings to perform the data transfer between the IDPs. And one thing you notice is the collision handling method for the hash join. So the linear probing shows the shortest latency compared to the quadratic probing and double hashing. However, in respect to the collision rate, linear probing shows the highest collision rate compared to the quadratic probing and double hashing. This is because linear probing is the simplest algorithm that do not use the complex arithmetic operations. However, quadratic probing uses the multiplying operation for finding the next bucket, and double hashing uses the modulo operations. So linear probing shows the shortest latency. And in the case of PPCH queries, we expect a 3.41 faster two-way join for the PPCH queries, and for in respect to the end speed up, we expect a 1.26 faster PPCH queries when included two-way join. And we also expect that there is a speed up and there is a multi-way join queries. So for the conclusion, PID is highly promising device for overcome the memory wall. However, firewalls commonly focus on the 3D step memory, and they only rely on those background simulations. So thus, this is the first study that which accelerate join on the PID-enabled DIMMs. And the PID-Join is the best ping-assisted join under the PID-enabled DIMMs. So it can achieve a joining speed up compared to the PRHO of 1.9. Thank you for listening, and this is the GitHub of the PID-Join. And thank you. I am happy to answer any questions.